think I even put the very first part on the board, how to calculate the value of A if you have a density function. I'm going to go through this real quick, but I'm not trying to criticize or anything. I'm just trying to find a way to encourage you, because this kind of stuff, that was meant to be super easy. And I didn't see that as a result, and I don't know what the problem is. So I'm just leveling with you from my perspective, because we're going to get through chapter 2, and we're going to be done with the different density functions, and then we get into things that get, in my opinion, much more conceptually difficult. So I'm trying to be clear about this. It's going to require a lot more time in the future. It's not going to be as easy as it's been. Anyway, for this problem, I said something. This is a brand new marker, by the way. All right, we'll try that. I said that we had a probability density function for x, and it was just a constant. I think it was from -1 to 1. And I put the value as A. Do you all agree? You all follow me? And I tried to put this thing up before in class to make sure that nobody was asleep when they took it. So if you have this, the number one thing with these is the integral of f of x dx. In this case, I can put from -infinity to infinity is 1. It's just the area under that curve has to be 1. There's no other way. And I can give you a functional form where you calculate the constant in front of a function, but this is about as easy as it gets. It's a box, in my opinion. So for this thing, if you look at this, the width is 2, the height is A, and that has to be 1. That means A is 1/2. And that was all there was to that. So now you got f of x is equal to 1/2 for x greater than 1, -1, less than 1, and 0 else. That's it. Now, the next thing I have is y is equal to x squared. And I asked you, do you all remember this one when we did this on the board? Not the lecture before, 2 lectures before that. We did this, and we literally did this problem, or actually we did a harder problem. We had a different density function. Do you remember doing this thing? How many do? I'm curious. You should all have a very clear memory of doing this in class, and the problems as well. I think that was in section 2-3. If you take a look at this, first thing I think, after you got A, then I wanted Fy of y. And this is the squared one. So you can see that x itself is equal to plus or minus the square root of y. That being the case, or you can say dx dy is equal to 1/2, and it's going to be plus or minus this. It's 1/2, 1 over the square root of y, or y to the -1. Do you all agree with this? Making sure there's nobody that doesn't see this. Now, when we want f of y here, because we have 2 values of x that gives us 1 value of y, we're going to have this basic relationship. You're going to have f of x with, and it's going to be minus square root of y plus f of x square root of y, and then you're going to have dx dy right there. Now these 2 values are going to be the same, so I can double. It doesn't matter which one you put in. You can double it because the density function is going to be constant. So you can take simply 2 times, and it's f of x. Well, x is just 2 times a here, or 2 times 1/2. And then it's times dx dy, which is going to be 2. And I really didn't care how you had that. Any form like that's fine. Do you agree, class? Did you have a question? Okay, everybody with me on this? I didn't care if you put y to the minus 1/2 on top or had 1 over square root, it didn't matter. So that's f of y. Then I think after that, the mean value for y, right? So that means the expected value for y. And that has to be an integral from 0 to 1 because y is strict positive. It has to be from 0 to 1, right? You all agree with what I'm saying here? All right, then you put in y, so I'm going to have, or the density function, 1/2, and it's going to be y here times y over the square root of y dy. And that's going to be 1/2, and then you're going to have square root of y dy integrated from 0 to 1. 1 over 2, and the integral of this, I'll put this up here. You get the integral of any function, in this case, I'll put x to the a dx in general. It's 1 over 1 plus a here, and it's going to be x plus a, 1 plus a. So this is going to be and for that one, would be 1/3. You don't need your calculators for really simple integrations. I think there were some people that got confused and they were trying to do the limits with x and use the function of y. So I'm telling you, you have to be careful about this stuff. Then it says, what is the mean squared value of y? Again, just an application right here. For the mean squared value, now the last part, this is the one where you could have done it a couple of different ways. And the last part is find the probability that y is less than 0.5. Well, here I'm going to come to here. If you think about y less than 0.5, I mean, I could literally say that probability right here of y less than 1/2 could be equal to the integral from 0 to 1/2 of 1 over 2 square root of y dy. That's one way to do it, and you surely can get the right answer. Another way, and I'm just mentioning this because later on this might come in handy when I'm telling you. When you think about this, if y is equal to 1/2, x is equal to plus or minus the square root of 1 over 2, or 0.707 plus or minus. Do you follow me on this, class? I'm trying to say this for a reason. Now, the reason I say that is if you look over here, the density function, if you take from minus 0.707 to plus 0.707, the area I have here is the same as the area you would get if you would basically do that integration. Do y'all follow me? I'm just telling you, now this integration is trivial, right? It's not bad, but you're gonna find out if you had like, say you had something where you had y, a log y kind of thing, where it's much more difficult, you could, by default, if you figured out that this thing was constant over here, you could easily get that just by looking at the area here. So try to think about the problem before you just brute force it. This was an easy one though. So for this one, it's gonna be what? 1/2, and then you're gonna get I think that's 0.707 something. You agree with that, class? All right. I would make a note on your quizzes that expect the density, if we're gonna get a problem like this in the future, expect this density function for the first function to be an actual function, something other than just a constant. Make sure you're aware of how to do those kind of problems, because those are the things I think that could trip people up real bad. Now, all right, enough about this. We'll put it behind us. I asked you to, yes, sir?
On the last one, I tried to do it that way where I like integrated over x instead of y.
Well, that's, hold it, you did this right here?
Yeah, like I switched it and, because I couldn't figure out the balance for y on the previous two, so I decided to use x. But I went from -1 to the square root of 1/2 instead of.
Why would you go from -1?
I just like assumed that, well, because like the inequality that I got was x is less than or equal to the square root of 1/2, so I figured -1 would be included in that.
No, x is going to have plus and minus values for any value of y. So if y is between, the probability for y between 0 and anything, it means x is going to have a minus and a plus value. Because if you have y equals x squared, you take the square roots of both sides. Square root of x squared on that is plus or minus, right? Square root of y. So you have to have a positive and a negative when you have a function like this that's going to be a squaring function.
That makes sense. I just was confused on why it wasn't included up to -1.
Well, it can't, because just think about it. If you have this, if y is 0.5, right? X would have two possible values. And x is going to have a lower value and an upper value. The lower is the -1/√2. The upper value is +1/√2. Down here, this is forbidden. If x is 1, y is 1. Follow me?
Okay.
You're way out of bounds there. It's got to be within the allowable limits. But the reason I'm mentioning this is, and I know this from experience, a lot of times when you get these, I mean, there's Gaussian functions you're going to find. You're not going to have closed form integrals of. I mean, you're going to have wild kind of things that you put them in your calculator, even that thing will cough. But oftentimes, you can come back on and take a look at the original, look at the question and see where the bounds are on the probability of, say, y can be any function of x. If it says y between like a and b, it's going to have x between a and b. Not exactly, but the inverse of that, right? When you have an even function for a function like a squaring function, if I say the probability of y between, say, 1/2 and 1, follow me? That's the same thing. Take the square root of that, and it's the same thing as x being between -1 and minus 0.707 and plus 0.707 to 1. You follow me? So you make sure you try to reason through it that way, because oftentimes, going back to the original density function is easier, and you'll see this shortly. Hopefully I get to it today. We're doing, like when you have power is equal to I squared R. Well, if you have a density function for I, and then I asked you what's the probability of the power between two ranges, say from 1 watt to 3 watts, it's now I would have values, but they're negative and positive. And you can easily get those kind of, you can easily look at the density function for I, and it's usually easier to get the evaluation of that probability than it is to look at the actual density function for power if you're going to derive it. Now, you'll see this in a bit. Anyway, today, I've got some stuff I want to cover. Did you all bring your calculators? I'm going to try to be clear. I'm going to turn the page. If you did bad, I feel bad for you. I don't know what else to say. Other than just leave it go, move on. But learn how to use your calculators now. I'm going to tell you, this stuff you can mess up on your calculators. I try to tell people from my past experience teaching this class what I've seen in problem areas so you can be aware of it and then adjust your study habits or whatever to it. This particular thing is, what I get on this, I get people, two-thirds of the class do absolutely perfect, and the other third do absolutely nothing right. And that's the problem when you have a calculator doing your math for you, you might say. Now, I used to give out tables. If anybody wants tables of the Gaussian integrations, normal stuff, I will provide them. But I think everybody's calculator does this. And I think it's a silly thing to hand out tables that will never be used in the real world. Have you all tried your calculators with the normal distribution? I want to make absolutely sure everybody does this. I'm going to, let's see, I'm going to do an example. First I'll put up the Gaussian distribution and stuff. I'm going to do an example. We're going to see that the Gaussian distribution is used to derive all these other distributions like the Rayleigh distribution, Maxwell, you know what Maxwell-Boltzmann is from the velocity distribution of gas molecules in space? Have you heard Maxwell-Boltzmann? All these things are derived from Gaussian. And in the book he talks about, if you read the sections on with the Gaussian distribution, the normal distribution, you saw that it's based really on physical observations and natural laws, and those things were derived in a brilliant way. By the way, you know, the name Gauss is kind of important. How many know who Gauss is? He's a mathematician, brilliant mathematician. I don't know if I told you the story about Gauss when he was a young kid. I don't think I did. Did I? Did he? So when I was in grade school, which is probably like you were, one of the things teachers did is they gave us an assignment to keep us busy so they could grade papers or something. Give us something to do. One of the things they loved doing, and I was brought up in a Catholic school system, is have us add a bunch of numbers together, tell them what the result was, and then go and hand the paper into the teacher. But it would take some time. So the thing that they did, I guess, way back when Gauss was a kid, supposedly in 2nd or 3rd grade, was have them add all the numbers from 0 to 100. And gave the problem to the kids, and anyway, Gauss gets up after about a minute, comes up and gives the answer to the teacher, and it was right. And as the story goes, that's when the teacher realized we're not dealing with the normal kid. Here's what Gauss did. He thought about it. He said, why would I brute force 1 + 2 + 3? If I write 0 to 100 this way, and then underneath it, 0 to 100 this way. You add up the columns, you get 100 each time, and there's 101 of them. Well, 101 times 100, you need to multiply. Straightforward, right? Right? And then divide that by 2, now you have that number. This is a math, it's a standard formula in math. And he brought it up to the teacher. So that's the level of intelligence this guy had when he came up with a lot of this stuff. The Gaussian distribution is one of I don't know how many different things that he's created based on, I would call it clever reasoning and making, he had insights that I don't think many people had. He was a gifted person. Anyway, enough about that. We know the density function for this, in general for Gaussian, is 1 over the square root of 2 pi here, sigma, and sigma is the standard deviation, exp, and it's minus x minus, I'm going to use u because your calculator uses u for the mean value. It's squared over 2 sigma squared. And that is the Gaussian distribution. Now, it's called a normal distribution or a bell curve. It looks just like a bell. If this is the mean, then we'll always have the peak value at the mean. And it will look like this. And there's some things I want to make sure you see. This is the density function, f of x. Always looks like this, always. When you look at this, the maximum value or height occurs when x is at the mean. That means the exponent here goes to 1. Y'all follow me? It means the value is just 1 over square root of 2 pi sigma. So this top value right here is 1 over the square root of 2 pi sigma. Now I'm telling you that because if I give you a bell curve, in other words, if you have a picture of that is there, then you know this value right here will give you the standard deviation. Can everybody see that? I just want to make sure. Y'all with me on this one? So if you see, say this value is 2, right off the bat, you can say, well, 2, right? Think about it. Multiply it by square root of 2 times, or square root of 2 pi, that's 1 over sigma. So 1 over 2 square root of 2 pi would be sigma. Y'all see that? You can get it just by looking. You can always get the mean value by seeing what number here is associated with that. So you can get the mean and the standard deviation. Are you with me? That means you have this expression. Just by, if they show you the curve, you've got the expression. That's the idea. Or if you have the expression, you can draw the curve. Either one. Now, some of the things that I didn't get at, but you have to see. This Gaussian curve, bell curve, is absolutely symmetric about the mean. Everybody with me on that? What that it tells you is this. If you come out from the mean any given distance, and you can call that distance k, it doesn't matter. Well, the area, if you take from the mean, if you go out k, the area above that is the same as the area here. All right. From minus infinity to u minus k is the same as the area under the curve, or the probability of the event being between u plus k to infinity. Can everybody follow me on this? I'm trying to make a point. The symmetry can be exploited. Now, and it's important to know that. When we do the nice thing about your calculators is you don't have to mess with tables and do all these adjustments. But there's the cumulative density function in your calculators, typically. And in here, they won't have just the value of x. They'll have x, and they'll have something like the mean, and then the standard deviation, I think. You have your calculators here. I want you to get them out in a second, because I want you to be able to do this accurately without mistakes. It'll be something like this. I don't know if it's CDF all the time, but it's something like this. All right, I got to ask a question. How many have the 36, TI 36? Do you? What do you have over here?
I have a TX Inspire, or TI Inspire.
An Inspire? Anybody have anything besides TI in here? I think it's called CDF.
I've got normal CDF.
Yeah.
Normal CDF? All right. But you should have 3 entries for a limit, and I'll put, what this really means is, it's the integral from minus infinity to x of f of x of x. In other words, this density function dx. So it's the probability of, what this is equating to is the probability of really from minus infinity, and it's going to be the probability from there to x, the probability from minus infinity to x of the event occurring. That's what it should be. But you should have two other values. And I think the next, is it the mean, the next one?
Mhm.
And then the standard deviation. Now make a note of this. That's standard deviation, not variance. Variance is squared. I mean, standard deviation is squared. You've got to be careful about this. So in the book, he talks about a function, and this is where we're going to normalize, but I'll just tell you what it is. It's equal to an integral of 1 over square root of 2 pi. Sigma will become, I mean, basically they're going to normalize this and take out sigma and take out the value of the standard deviation, or of the mean. And it's going to be exp to the minus x squared over 2 dx, and it goes from minus infinity to this function x here. But that function x is actually equal to the real x value minus the mean over the standard deviation. So this value of x, I wish they didn't use the same symbol, be changed. You're probably not going to use that. I'm mentioning this just because it's in the book, and also you'll see something like this discussed. Now, the whole idea behind this one is if you have tables, you want tables to get rid of any kind of effect of the mean and the standard deviation, or else they're worthless. You would have gigantic volumes of stuff. So they do that by making this variable right there a normalized variable. Subtract the mean from the value, divide by the standard deviation. Now, something to be said about this, that function, and in the book, I think he actually does this. He uses this symbol. I think he uses phi. I don't like that function because there's a function that's complementary to this as a q, and believe it or not, it's easy to write one as the other, vice versa. Now, what it says basically is if you have phi of, and this is the symmetry argument, phi of x, that's equal to 1 minus phi of minus x. And here's the reason why. But you'll see this may have some benefit in the problems we do using your calculator. You'll see. If this is x, and now we're just talking about phi of x, and this is a bell curve like so. Well, if you take a look at this right here, I said if, put it to a different way, phi of minus x is going to be 1 minus phi of x. I'm gonna, you'll see the point I'm making. So think about that. That function phi of x is really an integral from minus infinity up to a point. I'm just going to call this point A. So if you think about this, this is actually called minus A. If the area up to this point, right there, would be the same as the total area, right? If you think about this, minus the area all the way up to here. And that's what it's saying. In other words, the area down here will be equal to the area up here, and we can adjust the math as such. In the tabular form of this stuff, they'll never have values of minus the argument there. It'll always be plus. That's why if you do have a minus an argument, take 1 minus the value of the positive argument. That's the only reason for it. And I'm mentioning this because some of the problems we get into, I don't know if your calculators really have problems with it, but it might be easier to do something like that. And what it comes down to is now that I think about this, I don't think you're gonna have a reason for adjusting this when you do these problems, now that I think about it. Because yours do allow the mean and the standard deviation to be in, so that's not a problem. But what I'm going to get at is with your calculators at hand, we're gonna do some problems, and here's the thing we're gonna do. We're gonna make sure we can get the probability of something being from minus infinity to a point, then the probability of something being from this point to another point, and the probability of something being from an upper point to infinity, because that covers all three possibilities. And I'm saying this, and one of the things that I hope I never see from this group is the probability of something occurring being negative, I've had that a few times in here already, or the probability of something being greater than 1. You follow me? You've got to make sure, at least reasoning-wise, you know it is between 0 and 1. And anything outside that realm you throw out, and it can't be imaginary either. So I say these things just because I'm thinking of all the mistakes I've seen made in the past. We're gonna do a few problems. I'm not trying to just linger on this, but it's important. Are we finally done with baseball or not? It's over. I'm asking because I didn't go to these games. My friends did. All right. So the first problem, I'm going to do an example. And I know I asked you to do some problems, but I'm going to do an example. This is going to be the example that has mean value 1, a variance of 4, and they're going to ask some basic stuff. So this is, we've got this, it's a normal distribution, a Gaussian distribution. You know what f of x is, right? So f of x, I'm not going to ask you to rewrite this, but you should be fairly familiar with this. It's just 1 over square root of 2 pi sigma. But you should know this because if I just gave you a bell curve, you need to be able to obtain the information that's included here. Minus the quantity x minus u squared over 2 sigma squared. We know that's f of x. And then they say the probability, try this in your calculator, of x being less than 0. So I could do this on tables, but you know what you're really doing is taking that distribution and going from minus infinity to 0 of f of x dx. Now, if the mean was 0, that would be exactly 1/2. I'm making that point. If the mean was 0, then it would be 1/2. But for this one, what did we get?
0.3085.
I believe that's right. We did some of that, or one standard deviation away, and I asked what's the probability of being between 1 standard deviation, the mean, 2 and 3 standard deviations, just to make the point that if you're within 3 standard deviations of the mean, it's like 99.9% chance that it's there. All right, that's the first part. The next part, by the way, did everybody get that in your calculators? Anybody not get that? Okay. Then I'm going to ask, what's the probability of x being greater than 1 less than 3? Now, here you're going to have to put an upper and lower limited, and I don't know if they're both the same for the TI models or not. don't you have to enter two different limits on yours,
Mhm.
upper and lower? All right, what did you get to this?
0.341?
Anybody else?
What are we putting for you?
Huh?
What are we putting in for you?
The mean.
That's one.
That's one? Oh, okay.
Yeah. I'm expecting a few mistakes, but I'm just, did you get that?
Mhm.
Everybody get that? All right, now, for this one, normally, a way to do it is first evaluate just the cumulative distribution function at 3, and then subtract from it the cumulative distribution function at 1. That's allowable, you know? And the other thing is, if I said, what is the probability it's not between 1 and 3, you would just take 1 minus that. And I'm being, you know, I'm just saying the obvious. Everybody with me on this? I gave you some problems in the book. Were there any questions about this? Because, yes.
Whenever we are given the probability and we have to work backwards,
Oh, that's an interpolation. That's an inverse function. All right, that's a good point, yeah. I will do that. And what he said is, I've got a problem with this. Yeah, the inverse is important. In tables, in the book, he discusses how to use tables to do that, I think.
Yeah.
All right, you have a calculator. You should have an inverse function for your cumulative distribution function. I think. I use it with normalized stuff. Now yours will be different, I think. So is this, I have problem 251, 2-5.1 I've worked out, but I don't think that's
no, that's not. I think it's on 2-5.3.
2-5.3, all right. So for that one, I've got that one too. Yeah, let's do that one. And a lot of times the problem can be worded in a way you have to have a working knowledge of what it's going on. Remember how I told you with the bell curve, you have to be able to just look at a bell curve, get the standard deviation from the peak, and then the mean value just from where it's the maximum. You have to be able to do that. So for 2-5.3, do you have it in front of you?
Gaussian random current has a probability of 1/2 of having value less than or equal to 1.
So that's the mean value of the current is 1 then. What he said is, if they state in the problem that the probability of something is 1/2, whatever that something is, that tells you where the mean is. In this case, it says of the current having a value of 1, right?
Less than or equal to 1, yes.
All right, so that means the mean value would be 1. And what he's really doing is, if here's 1, and this is the current value, he's saying the current density function of I this has to be 1 because it's got exactly the probability of being 1/2 of the area under the curve is below that or at that point. What's the other part?
It also has a probability of 0.0228 of having a value greater than 5.
Okay. Yeah. So then after that, he's saying the probability that the current is greater than, what was it?
5.
5 is
0.0228.
now what with well, let me say this. So now when I take a look at the actual normalization function that I use, you don't need to use this, but I'm going to just tell you this, and you'll see how it overlays onto what your calculators do. If you take a look at this, there's a function, the phi of x function I put down was really the integral from minus infinity to something where now x in this argument became the actual value minus u over the standard deviation. And this would be f of x dx. But this is using a normalization, so it really became the integral from minus infinity to this value of x there of 1 over square root of 2 pi. That's going to be times exp minus x squared over 2 dx. But there's something called a complementary function, and he calls it q of x. And that's equal to the integral from x to infinity of this 1 over the square root of 2 pi exp minus x squared over 2 dx. And the thing about it, and it'll be obvious, is that I can take a look at this function right here. Now he has tables with this value in them and tables with this value in them. But for this one, in the tabular way to do it is, what I would do is create the variable x is equal to 5 right here, minus the mean value, which is 1, over the standard. He must have given a standard deviation. Oh, he wants us to calculate the standard deviation, correct? Yeah. So he wants this. And since we know this value right here, we can get the value of q, and basically we can get the x value right here that makes that such. Now, in your cumulative distribution function, I believe you can go ahead and get the actual argument of the cumulative distribution function. I erased that thing that would give you this value. But let me just say one thing. We're after the standard deviation, right? Okay, we got the mean value. So if you look in here, remember this. This function right here is equal to 1 minus q of x. Let me just say this. I think there's two ways to do this. With your function, because your cumulative distribution function right here of x, u, and sigma is equal to the integral from minus infinity to x of that f of x dx. There's a complementary function you have also. But what you can do is simply say that 1 minus the cumulative distribution function of x, u, and sigma would be equal to 0.0228. And then that would give you the cumulative distribution function and I'm not sure if your calculators would be able to do. Will they do the inverse of this?
Mine can, it's called the inverse normal.
And when you get the argument, you put in a value for u, right?
Mm-hmm.
Right?
Yeah.
And you put in a value for x, 5, right?
It says area.
You put in the variance and the mean, and then.
But we don't know the variance.
And then you put
Standard
in
deviation.
standard deviation, sorry.
What's that? You put in the standard deviation.
I guess it,
Hold it, we don't have the standard, we're trying to do the inverse.
yeah, That's what I was confused about.
Okay. All right, so yours doesn't allow you to put in the value of X and U and get the standard deviation, is that right?
It wants area, standard deviation, and mean.
Well, that's the area.
Mhm.
All right, well, then you can do it, I'm almost positive there's a way to do this, but with your calculus, I just don't know it. But I'll tell you how you can do it, and I'll make it real simple. So, I'm not even gonna bother with that. I'm gonna come over here, and what I'm gonna do is say that I'm going back to what I know, and that's the Q function. I know or actually, because in your case, it'll be a cumulative distribution function. I know this, the normalized value of this. I'm using X here, but this is actually, X there is the actual value of X minus mu over sigma. So keep that in mind. That is equal to the integral from minus infinity to X of the normalized thing, which is 1 over square root of 2 pi. That's going to be times exp minus x squared over 2 dx. I'll get to the point, I'll slow down in a second, but that is the definition of the normalized integration of this. It gets rid of everything. And for your calculation, the mu on this one would be 0 and sigma would be 1, basically. This is the same thing as your cumulative distribution function with a mu of 0 and a sigma of 1. Following? Now, for this one, we know 1 minus this value, phi of x, is going to be equal to 0.0228, which means phi of x is equal to 1 minus 0.0228. I'm just getting it down to, this is normalized here, and you'll see, and I want you to make sure you use your calculation to do this. So, come over here, and the only thing I want, and you can do this with yours, if you take a look at this, or I can look it up in a table, what is the value over here? 0.9772? All right, so that's phi of x. Now, take the inverse cumulative distribution function with mu equals 0, sigma equals 1, and give me the value for x here. Everybody understand what I'm doing here?
I'm confused. Why do you assume that mu is equal to 0?
Because what I'm doing right here is, in the book they talk about this. This is called a normalized distribution. It's really, he uses a symbol for it. So basically, if this argument goes here, what I've really done is I've taken the regular distribution function and I've gotten rid of both the mean and the standard deviation, and I adjust this value accordingly. So it's still the same point in the bell curve, but now I don't have to worry about the mean or the standard deviation. So having said that, this one right here is like your cumulative distribution function with mu equals 0, sigma is 1, but we're not done yet, all right? Now, once we get there, can you give me that value?
I think it's 2.
Well,
It's like 1.999077.
it's about 2.
Yeah.
About 2. Now you come over here, that's this value right here. You follow me? So now I say 2 is equal to, they give us a value of 5, right? The actual value of the current was 5 or greater, right? So now I put in the 5. They give us the value, or we figured out the value of the mean as 1, right? And now we can get the standard deviation. So the standard deviation is going to be equal to 5 minus 1 over 2 or 2. Do you agree with that? Is that the right answer?
Yes.
All right, now I want to do another problem like that because you're going to be clumsy about this until you do a few. But here, it's the inverse problem. It's the same exact technique. Yes, sir.
What's the difference between Q of X and phi of x.
All right, Q
Because it's just-
starts at x, goes to infinity. Phi, right here, starts from minus infinity x. So Q of x, you should say, I should say this, phi of, by the way, I don't like these symbols, plus Q of x equal 1.
Okay, so
That's
it's just
the-
like half of each of the bell curve.
You're either above it or below that point. And if the area under all of it has to be 1. That's the expression. But he has tables for both of those. That's the reason I'm making a point of this. Your calculators will do this, but I want to do another problem like this because this is a good problem because it's the inverse. Now, I think, and I'm saying this carefully because I'm not sure, but I believe your calculators do have the ability. So if you know the value, so if you want the inverse and you want them to calculate the standard deviation, I can't prove that, by the way, because this is just from memory from a while ago. You can put in like, you got the area on one side, so for this function, you would have the area over here, whatever it is, like point, what was it, 9772, right? Then you would calculate the unknown. You don't know x, or I'm sorry, you know x is 5, you know u is 1, and it would give you sigma. I believe there is a way to do that in your calculators, but if you don't know how, go to the normalization route, because it's easier that way, at least to see it in your mind.
Does it work for both sides of the curve, I guess? Like, you can always put that mu is equal to 0, sigma equal to 1.
Here's what I'm effectively doing. I'm evaluating either this is a cumulative distribution function with mu equals 0 and sigma's 1, right? But what I've done is adjust this value so that everything works. I've adjusted the x, or the argument there. And I didn't prove this, but if you go ahead and suppose I put this in right there for x. If I put x minus u over sigma, right? Then I come over here, and everywhere there's an x, I put x minus mu over sigma, and I square it. I will get exactly the distribution function that I wanted. And then the limits here, this value of x would be replaced by the x minus u over sigma, and when you do everything, this value is adjusted and it comes up perfect. Right? But it's at least getting the inverse, if you're not familiar with it, it's probably easier doing this, basically doing the normalization and then figuring out, once you have this value, what sigma is, or once you have this value, what u is. That's my opinion. Is there another problem that does this in this section? But that's a good problem. I want to do at least one more like this. I didn't get into the central moment thing. I think we should do another one. Here's something, thinking about it. When you have to do an inverse kind of problem. If you said that there's a Gaussian distribution for, say, X. So I'm gonna have it's Gaussian. I have an F of X here that would be 1 over the square root of 2 pi sigma EXP to the minus quantity X minus X bar, or mu, I should say, mu squared over 2 sigma squared. That's it. And then I say this is going to be a little different. So I'm going to say that make this 2, that the probability that X is greater than or equal to 2 is equal to 1/3 and the probability that X is less than or equal to 0 is 1/3. Do y'all follow me on this? Now, I want you to tell me the mean and the standard deviation. Think about it first, and drawing a picture helps. All right, what am I really saying? There's a mean here, right? So my distance from here to here will be the same distance as from here to here. And the area here will be equal to the area here. Do y'all follow me on what I'm saying? Just think about this. Now, there's one thing you know for sure. Because, and this isn't exactly looking symmetric, but it's supposed to be, that this is supposed to be that folded, right? So what does that also tell you? Well, if I do normalization, just listen now. If I do normalization, I can go ahead and figure out what the inverse of 1/3 is here, right? Do y'all agree with this? And I can figure out the inverse of 1/3 here, right? Follow me? I don't know what the mean is, but I do know that that's 2. And I know from 2 upward, it's going to have that value. So, I guess what I should say, I'm saying this in a way that when I take a look at this, my phi of x is equal to the integral from minus infinity to the point, and I'm going to call this spread k here. And I'll use u for this. So this distance is k, and this distance here is going to be k. So this distance is going to be u minus k. Now I can say the integral from minus infinity to the mean minus k of this. Oh, what am I doing? I'll normalize right away. Make it easy. So now I'll say that x is equal to x minus the mean over sigma. So I can say the integral from, or what I want to do is get this lower limit. two x, one over square root of two pi times exp minus x squared over two dx would be equal to 2/3. That wouldn't be x actually. It would be u minus x.
Minus K.
Okay, it's gonna be u minus k here, and this would be u plus k. But if you tell me, actually, what we can do, making this much harder than it needs to be. If you take a look at this, just give me the inverse of this one, your cumulative distribution function of, with mu equals 0, sigma equals 1, the inverse of this f of x normalized dx equal 2/3. Just tell me the argument of that. So the cumulative distribution function for, I want to know the value of x if mu is 0 and sigma is 1. Can you tell me that?
I think it's 0.431.
Is that right? All right, so if we have that, 0.431 is equal to x minus the mean over the standard deviation, right there, and then, because of symmetry, that's 2/3. Oh, yeah. So, at this point, I'm trying to find words for this in this inverse. Let me just do this real quick. So this is if it's normalized. Here's what I'm getting at. I know, here's what I'm really getting is the symmetry argument. Once we do this and, we're talking about using a normalized thing, so you get rid of sigma, get rid of the mu, right? Then I know that I got a third above here, a third above here, right? And this would be a minus value. So that tells me there's 1/3 between here and here. Y'all follow me on this? Now, that should be more than enough to get the information we need. And I said that was for x equals 2, so I have 2 here. I have one equation for that, and I also know that the area, the cumulative distribution function from minus infinity to this point is going to be 1/3, and that should be 2 equations with 2 unknowns. be sure about this thing. So then 2 plus u, wait a second. No, that's not right. Okay, one last look at this thing. All right. We got that point, that would be 2 minus u over sigma is that. And I know that's the same thing. That's also the same thing as 0.4. Oh, yeah, yeah, yeah. That's 2/3. What's the value of the inverse of the cumulative distribution function for mu equals 0, sigma equals 1? I'm sorry, I'm messing this up. If it's equal to 1/3, that was for 2/3. What do you get the value of x? Then we have it. I'm sorry about that. Now I'm talking about this down here. I'll try to be clear.
The negative number of that same, or negative 0.431.
So then you're going to have minus 0.431. That's the error, or that would be the value of x, right, after normalization, is going to be equal to, and here, it's 0 minus u over sigma. Do y'all follow me? What I've done here is, remember the way when I do this normalization, so it didn't dawn on me sooner, when I have, what I'm going to do is replace the argument for my phi function. This right here is normalized, it's phi of x, but I replace that argument with the value of x that I'm using minus u, whatever it is, divided by sigma. So when we took a look at, we got this value, when x was 2, we knew it was 1/3. Above that, or I should say it was 2/3 if we use the cumulative. But basically, we get one value for the 1/3 when it's a value of x is 2 or greater than it's 1/3. Then we look from minus infinity to 0, and that value is 1/3 as well. And that was this one. Now we have two equations with two unknowns, so we can solve it. What do you actually get for this? This one's straightforward because I got a 0 there, right? So I multiply that by sigma and I get simply that u, the mean, is equal to 0.431. And that gives you the value of sigma, right? Therefore, sigma is equal to 2. Wait a second. Sorry, it would be minus 431 sigma. So then I get 0.431 is equal to 2 minus 0.431 sigma over sigma. And now you can solve for sigma. I'm not sure what that comes to. Put a sigma over here. And you're going to have sigma is equal to 2 over And that's gonna be 1 plus 0.431. Unless I made a mistake. Now, what does that come to? It's two equations with two unknowns. I'm sorry I messed that up. Do you follow what I'm trying to do here? Yes, sir.
So you just took the lower side of x is less than or equal to 0, and you said everything to the left of x is less than or equal to 0 is 1/3, and everything to the right is 2/3.
Well, yeah, well, actually, you're absolutely right about that. What I'm saying is based on the statement of the problem, from minus infinity to 0, there's 1/3 of the area under the density function. And from 2, the value of 2 up to infinity, that area is 1/3 as well. And the only thing I did, I'm sorry I fumbled this thing, but now I use the normal distribution thing to figure out, since the commutative distribution function that I have integrates from minus infinity to a point, but I'm normalizing that. So I said if I take 1 minus the value of that, I would get 1/3, and I need the value of the argument of x that gives me that. And here's what I'm really trying to say in so many words. This value and this value that I have are all for the normal distribution. So I know this value right here, that value of x has to do with, based on this, x is equal to the argument there, which is minus 0.432, has to deal with x minus u over sigma, right? Forget this one. All right, this value of x that rendered that was 0. Then on the other one, when I had 0.432, there's a value of x here, and I'm going to put it in minus u over sigma. This value of x was 2.
But how is it 0.432?
Remember, we calculated the reason the normalized value would have this value is the area from this point on.
But the area is 1/3, so.
Right, 1/3, we did the inverse to get this.
But if you do it with 1/3, we did it with 2/3 and got the positive.
No, well, the area is 1/3, but for the cumulative distribution function, you have to take 1, and it would be, if you think about this, 1 minus 1/3 is 2/3, would be the cumulative distribution function up to that point. Do you follow me on that?
Yeah, I'm just confused on, because if you just do it with 1/3 on both of them, you get the same, I guess, point at negative 0.
No, one's negative. This is negative, that's positive.
So you just did the CDF with the normal.
Yeah, but I could have just taken this value, since this is normalized, and make it negative. I know they're symmetric for the normalized, right?
Yeah.
I didn't do that, I should have. If I took these two, and I know these two things, I know this one corresponds to the value of x equals 2. Right, so I got 2 minus u over sigma. This one corresponds to the value of x equals 0 from the statement of the problem. Remember?
Yeah.
I promise you it works, and I'm sorry I fumbled it. I was trying to, as I was doing that, I was thinking of a way to do this with just one equation, but I couldn't. There may be, you have to get 2 points, and you have to use it, but that will get it every time. And you can actually plug that in there. What did we get the value of sigma over here, Bella?
I got 2.32019.
2 point what?
2.32019.
And what does that come out to the value of the mean? That's standard deviation. The mean would be 0.431 times sigma. So what is that going to be? I want to just finish this problem. I know. Is it 1?
It's 1.
Okay, that's what I thought it would be. Here's what I was trying to do in the beginning. I was trying to get something where I had a mean of 1, and I know I wanted the standard deviation to be very, I knew it was about 1, so if I go from 2 on up, or from 0, or from minus infinity to 0, I'd have the same area based on symmetry. But anyway, having said all that, if you plug this, let me finish this one thought, and then I'll get to you. If you actually plug in, just try this on your calculators. Go the cumulative distribution function and put in the value of 2, put in the value of u equal 1, and put in a standard deviation of 2.32019, and you should get 2/3. If we did this right. Anybody?
So 2.32019. You said 2/3, right?
Tell me what you get.
I get like 0.666765, so it's like, it's close to 2/3.
Yeah, that's very close. Yeah, you're gonna get that. That's sort of one of these things where we really need 2 points, because the normalization, the way I'm doing it, when you have the normalization, you're always gonna have the x right here, the x minus the mean over sigma. And you know, the area from minus infinity to this would be the negative value of that, is the same thing as the area from this value to positive infinity, actual value. And just exploiting symmetry. Took me a while, I'm sorry it took me that long to see that. I ran over, I owe you a few minutes. What I'm gonna do next time is finish this up with the moments. There's second and third order moments, actually third and fourth order moments and central moments. Then we're gonna get into the Rayleigh distribution next time. And I'm gonna try to show you some things to be aware of. That problem though that I just put up there, that's a good problem. And that's the kind of thing you can stumble on a quiz too. Because it's the wording. I'm glad I put that up there. I'll give you some more, and I owe you some time.
I was gonna ask, since that L curve is normalized, would the mean not equal 1 right there, for like that part of the equation?
If it's normalized, or if the mean's 0, that's what it means. Here, I'll show you. I mean, it's actually, that problem, sorry. It's not that. When you take a look at the standard cumulative distribution function of x, u, and sigma, in your book, it's got this. X, or I should say in your calculator, and it's going to be 1 over square root of 2 pi, and then there's a sigma here, and then exp, the minus the 1, x minus the mean squared over 2 sigma squared, dx, that's by definition. When you're dealing with a normalized thing, and maybe I shouldn't even use this, how about, it's another symbol, call it y. Y here would be equal to x minus the mean over sigma. Now when you do that, what you're doing is adjusting this argument, like this argument, so that these two integrations are going to be the same. So when you do that, you're going to get the integral from minus infinity to y, that's y. Now this function becomes 1 over the square root of 2 pi exp to the minus just, and this would be just y squared over 2 dy. Technically I should prime that, but what I've done is eliminated both the mean and sigma for this integration, but the results of this will be the same as that.
So you're almost like whenever you normal or do the inverse of that, you're taking.
Then I
the
just take,
inverse
I
of-
take the inverse of this, and I get this value of y. Now, when I get this value of y, I can get u and sigma, because I have the value of x up here to give that. So the problem we did, when I said for x greater than 2, I mean, the area above it's 1/3, means the area below it's 2/3. So what I did is, I knew it would be this cumulative distribution function of 2 u sigma that I didn't know was going to be 2/3. I'll come down here, and I said, I frankly, I don't know what u and sigma is, but I knew that x is 2, right?
Mhm.
So I can put the x is 2 down here if I want. And then I knew that was going to be, that's 2/3, and I get the inverse of this, so I found my value of y equals 0.431.
So you plug in the 2/3 for x, like kind of like the x part on the CDF once you've normalized it?
No, the 2/3 is the area from minus infinity to the value of 2, right? There's 1/3 above that. So,
Oh, I see what you're saying.
so there's 2/3 below that. That's what I'm using here. Now, I come over here, and I know that's the same thing as this integral being evaluated to some value of y that I don't know. So now I take the inverse of this, and I know that's got a mean value of 0 and standard deviation 1, and I get that value for y. Well, I know that y corresponds to this, so I say 0.431 is equal to 2 minus u, I don't know what u is, over sigma. Got one equation that I know. Then I come here, and I know the CDF of, this is 0 u sigma equals 1/3. Since I know that, I come over here, and I say, I want to know what y is right here. When phi of y is equal to 1/3, the argument for y is going to be 0.431, but it's negative. So now, that one is negative, and that has this has a 0 mean, so it's skewed down, it makes sense. But what that right there corresponds to the equation right here, which is going to be minus 0.431 is equal to, and the x, remember the x is 0, so it's 0 minus mu over sigma.
That's your second equation.
Yeah, and I should have seen this. There's a lot going through my mind. When I was doing it, I know there's a simple way to do a trick here, and I forgot what it was. So this is a brute force way. There is a way to do symmetry arguments here. But since it's 1/3 below and it's 0, and 1/3 above and it's 2, the mean is actually just the limits. Since they're same area above and below, the only thing you take is the lower limit, 0, upper limit 2, divide by 2, it's 1. But that didn't occur to me.
Yeah.
Because
that makes
it's-
sense.
it's-
Because it's symmetrical.
Yes, and sorry, when you're in front of people, sometimes it doesn't happen. But this one's pretty straightforward. Get rid of the 0, get rid of the negative. And I got u equals 0.43 sigma, and you can solve for both then. But it is on it, I know on an exam or a quiz or something like this, if you don't have, if you try to just brute force it, it can often just take forever. You almost have to stand back. Anyway, I'm glad we did that problem.
Thank you.
Anyway,